Hello guys, how are you today? So today I'll be explaining the chapter 3 course question document or course questions for physics. It's only from 3.1 until 3.10, so hopefully they are gonna be good and easy. They told us define magnetism. Magnetism is very simply a phenomena in which a material acts the same as a magnet, or it attracts ferromagnetic materials or another magnet. So to define magnetism, we can say it is the phenomena in which something acts like a magnet. This is very simply how we can explain magnetism. Now in part B, what are ferromagnetic materials? Very simply, ferromagnetic materials are materials that are attracted by magnet, but not only attracted, they are strongly attracted. So ferromagnetic materials, they are strongly attracted to magnets. Okay, moving on to part C. In what ways can permanent magnets lose their magnetism, or in other terms, this is demagnetization? Okay, there are many ways to do it. So you could have an alternating current, okay, or you could have knocked it, dropped it. You could have exposed it to heat or heating it extreme, okay, and many other ways, but these four types are the most important and the most well-known ways of demagnetization. So this is number one done. We move on to number two. They said describe magnetic materials. Magnetic materials are also what? Ferromagnetic materials. So magnetic or ferromagnetic are both the same thing, and they are both strongly attracted to magnets. Okay, now examples of magnetic or ferromagnetic materials are cobalt, nickel, steel, iron oxide to be more specific. Oh, and by the way, one more thing, something new, which is ceramics. I don't think they would bring this in the exam unless they say that ceramics is one of the things that is attracted to magnetic material. So when you think of ceramics, you'll think of like a plate, a ceramic plate. Well, yeah, but at the same time, no, this is not what it means. Ceramic in this case means like they pressurize some powders, usually metal or whatever, to form solid bodies. So these ceramics, in addition to iron oxide, steel, nickel, and cobalt, are ferromagnetic material. Okay? So poles of a magnet. You are supplied with two identical rods. One of them is magnetic and the other is just a steel rod. Suggest a way to determine which is what in one and only one simple move. Okay, now this one is a bit tricky, but let me draw what they told us. So we have two rods, rod number one over here, we don't know if it's magnetic or not, and rod number two, they're identical, we don't know if it's magnetic or not. Using only one move, they want us to suggest a way to determine which is a magnetic material and which one is not a magnetic material. So what we are gonna do is that we are gonna take any of the rods, let's say rod 1 and rod 2. Let's say we are gonna take rod 1 and we will place it at the center of rod 2. Why is that? Because in the center, the magnetic fields don't really do much for us. So let's say we put rod 1 to rod 2. If they attract, okay, that means this is a magnetic rod. How do you know? Because the force will come like this, okay? We know it will go always from the south side to the north side and then back, okay? So since it's coming, it's gonna attract it, and thus we know that this is magnetic. However, if you put instead 2 to 1 and it does not attract, this simply means that 2 is what? 2 is the plain steel rod, okay? Because the magnetic forces are not strong enough to attract it, or they are not like passing through, or in another term, the steel is not passing through the magnetic field so that it is attracted to it. That means this over here is what? This is the magnet, and this is just the plain steel. Okay? Moving on to question number 4. What are the two poles of a magnet and how can one identify them? Very simply, the two poles are north and south pole. Okay, so how do we know which one is the north pole and which one is the south pole? They said to us, freely suspend a magnet. So you're gonna tie a magnet to something. This is how I believe they did it. They're gonna tie a magnet, okay? Let us say they tied it like this. Okay, and they are saying that the extremity that is north is gonna go to the north side, whereas the extremity that is south is gonna go to the south side. So if it was hung like this, okay, and the south was on top and the north was on the bottom, it would then flip in some sense like this, okay, and then you get the north at the top and then the south at the bottom. Question number 5. Can we isolate a single magnetic pole by breaking a bar magnet in half? Actually, no, because if you remember in the quiz, we had a magnet like this, north, south, and then they broke it into two pieces and they said, what are the other extremities? This was north and south, this one was south and north, if I'm not mistaken. So basically, if you break a magnet, it will just form many other smaller magnets, because there cannot be only one single pole, so you cannot have north only. What will the north do by itself? It's not gonna do anything. There's no magnetic field. You cannot have only south. What will the south do by itself? There's no magnetic field created. So there's no such point in it not existing as a dipole, which is what? North and south. Okay. Question number 6. How do magnets attract each other? How do they interact with each other? This is a very simple explanation. If they have the same poles, they are gonna repel. If they have different poles, they are gonna attract. So north, north, south, south, repel. Okay, and then north, south, or south, north, they attract. Okay, so we move on to section 3.3. Construct a table that shows the difference between soft and hard magnets. So let us draw a table. Okay, here we have statement, and here we have type of magnetic material. So let us divide it into two. We have the hard magnets and the soft magnets. Okay, so we have hard magnets. They are first difficult to magnetize, okay, in the beginning. Then once they are magnetized, they are difficult to demagnetize. Okay? So some examples of hard magnets are hard steel, permanent magnets. All of these types are what? They are all types of hard magnets. For the soft magnets, however, we have an example to be soft iron. They're not used in permanent magnets, they're used for temporary magnets. But the soft magnets, they are easy to magnetize and demagnetize. So it's literally just the opposite of the hard magnets. That's pretty much it for number 7. Let us go to number 8. What is magnetic induction and what are the types of magnetic material? Magnetic induction is when a magnet attracts a ferromagnetic and it will behave like a magnet. For example, you have a bar magnet. Okay. Now what's gonna happen is that, let's say you have a paper clip attracted here. It's gonna become a magnet. It's gonna attract another, etc. So what's gonna happen is the magnetism or magnetic flux, it's not really magnetic flux, but the flow of magnetism is gonna flow through this one and this one and this one and this one. So they are all gonna become part of the magnet. This is how I understand magnetic induction. Or if you remember how induction would be the flow of heat, Yeah, it's the same thing with this. Okay, and what are the types of magnetic material? We have only two types, which are hard and soft magnetic material. Examples of hard steel, and soft would be soft iron. Okay, now we move on to 3.4, magnetic field and theory of magnetism. A magnetic field B exerts a force of magnitude 3 newtons to the north on a given magnetic pole P, and another field B prime simultaneously exerts a force of magnitude 4 newtons on P on an in an eastern direction. Find the direction of the resultant magnetic field if P is a north pole. So if P is a north pole, that means everything is gonna go towards the north. So if we are talking about north, east, south, west. Okay, so north, east, south, west. These are the directions if it is facing north. However, if it is facing south, the directions are gonna be like this: south, west, north, and east. So basically it's just gonna flip, okay? So they said find the direction of the resultant magnetic field if P is a north pole. If P is a north pole, everything goes regularly. So 3 newtons to the north, this is 3 newtons, and 4 newtons to the east. They need us to find the angle, or sorry, not the angle, the direction. The direction which contains the angle, that is the resultant force, okay, or the resultant magnetic field. Very simply, what we are gonna do is we are gonna find the value of the angle between the east and the north. So this is north, this is east. To find that, we are gonna do tangent inverse the y, which in this case is 3 newtons, over the x, which in this case is 4 newtons. So if you do it on your calculator, shift tangent 3 over 4, so you are gonna get an answer of 37 degrees. Now, always, we start with the east and west directions. So when we are gonna say the direction of the resultant magnetic field, we are gonna say, first of all, it's going to the east, and then we put the angle, which is 37 degrees, and whether it's north or south, in this case it is north. So the direction, if it is a north pole, is E 37 degrees north. Now, the direction, if it is a south pole, again, they said that it is 3 newtons on a given magnetic pole P towards the north. And north, we know regularly it goes up. Okay? And then they said 4 newtons towards the east. So we are just gonna do it in the regular direction. So we are gonna get here 3 newtons north and 4 newtons east. Sorry for that. Okay? So here we have kind of a small confusion, a small trick. We said that when we are dealing with south, the directions are gonna be the opposite. So first we're gonna put them normally. It goes north up and east to the right. But since we are dealing with a south pole, this becomes the south, okay, and this becomes the west. Okay, now to find the resultant, again, we are gonna do tan inverse of 3 over 4, so y over x, to get 37 degrees. And if we are gonna put the direction of the resultant magnetic field, we're always starting with west and east, so it's gonna be west in this case. Then the angle 37 degrees, and whether it's north or south, in this case it is south. Okay, so we finished question number 9. We move on to question number 10. Define a magnetic field and identify its direction. Now, the magnetic field is the space around the magnet, okay? That is the reason of the force exerted on any ferromagnetic material. So if we want to define a magnetic field, what we can write is that it is the space around the magnet that causes magnetism. That causes magnetism. Now, how do we find its direction? Very simply, to find its direction, it is usually the direction, so let me just write, direction of the magnetic field is the direction of the force exerted on North Pole. So let us say we have the case of this type of magnet. We have north here, south here. We know inside the magnet it's going from the south to the north. So the direction of the magnetic field is going to be the force exerted on the north, which in this case is going to the left, so it's going to be leftwards. Now, if it was the opposite, so let's say it was like south-north, then it would be going in the opposite direction. So the force would be to the right, rightwards. Very simply, this is what they mean for question number 10. Now we move on to 3.5 magnetic field lines. The south pole of a plotting compass points east at a certain point. What is the direction of the magnetic field on that point? Now here, very simply, we're just gonna go back to what we said above. They said what? We said in question number 10 that the direction of the magnetic field is the direction of the force exerted on the north pole. So let us draw a magnet. This is a magnet. Okay, it is always the direction of the force exerted on the north pole. So here they are saying that the south pole, okay, of a plotting compass points east. So where is the plotting compass? We're just gonna put it here, for example, the plotting compass. And they said that the south pole plots east. This is the south pole of the plotting compass. They said, what is the direction of the magnetic field? We know that the direction of the magnetic field is the direction of the force exerted on the north pole. So the south pole is going to be following this direction or this magnetic field, whereas the north pole over here is going to be following this direction or this magnetic field. So in this case, it is pointing to the west direction. So this is north, east, southwest. It's pointing to the west direction. You could do it like this, or you could memorize that the south pole, okay, of the compass has a direction opposite of the magnetic field, okay? So south pole direction is opposite of magnetic field, whereas the north pole, okay, has a direction equal to the magnetic field. Okay, so we move on to question number 12. They said in question number 12, describe and draw the magnetic field lines of a bar magnet. Very simply, we will draw a bar magnet. Okay, we have north, south. We know that inside the magnet, it will be going from the south to the north, okay? And we know that the magnetic field lines are smooth, imaginary lines, okay? And they never cross each other. They are also vectors, meaning they have a direction. So you always have to put an arrow for the field lines, and they should not cross each other. This is very important. So you could draw it like this, okay? This is a more complex way of drawing it. So you will draw that it will go in from the south towards the north, and then you can draw another one going in like this, and then out like this, and then it's going again in like this, and then out like this. And then we have on the sides, it's going from the north to the south, north to the south, and then here north to the south, and north to the south. Now notice when I drew it, no two magnetic field lines crossed each other, because if they cross each other, that means it is wrong. So they never, ever cross each other. So this is it for question number 12. We move on to question number 13. They said, draw the magnetic flux pattern of a U-shaped magnet. Very simply, I'm gonna just draw a U-shaped magnet. Make it a bit smaller. Okay, this is a U-shaped magnet. Let's say this is the north pole, this is the south pole. In between them, okay, it's going from the north to the south. They are parallel and uniform. Then when they reach the end, they start to curve like this, like this, like this, and so on and so forth. So basically, this is how a U-shaped magnetic flux look like. Now, in question number 14, they said, draw the magnetic field lines pattern between the unlike poles of two magnets facing each other. Very simply, I'm just gonna draw two magnets. So, magnet 1, north, south, magnet 2, north, south. So we have unlike poles facing each other. And we know that If it's not inside the magnet, it's gonna go from the north to the south. So outside of the magnet, it goes from the north to the south. So it goes like this, like this, like this, okay? And then this one comes like this, like this. This one comes like, sorry, no, this one goes like this and like this. And so basically, because there is a force of attraction between these two, the two magnets will attract each other and it will come like this, north, south, north, south. Okay, so that is 3.6 done. We move on to section 3.7, magnetic shielding. They said, explain the following statement that field lines never intersect. Very simply, what you can say is that when drawing the magnetic field, we can have only one resultant magnetic field at any point. So if they intersect, okay, it will have two different directions, which contradicts the everything we have been learning so far. Okay, so it's technically impossible for it to happen. So in words, to explain this statement, we will say that a magnetic field is resultant at any point as one. Meaning, at any point, a magnetic field becomes resultant, but it is only one magnetic field. Okay, so if they intersect or they cross, okay, this would form two different directions. This would form two directions. Okay, I'll just continue here. Contradicting the rules of magnetism. Okay, so you just write it like this, you are gonna get the full mark. Now describe a method used to map magnetic field. So there's actually many methods used to map magnetic field, but the most common method is using a plotting compass. So what you're gonna do is you're gonna place a plotting compass at a point through which it's like on this point, it is the point that you want to plot the line, okay? So the tip of the north pole of the needle, okay, is that point, all right? Then you have to draw a little arrow showing the direction in which the north pole points. After that, you have to move the plotting compass so the south pole is on the little arrow that you drew. Then draw another arrow where the tip of the north pole is. Then you're gonna move the compass to the new arrow, okay, drawn in step 2, and you're gonna draw a new arrow based on the north pole. So you're gonna continue this until you get the direction of the north pole. So let's say you have a magnet over here, okay. You take a plotting compass and then you wait for the north pole to be directed like this. Then after you do this, you're gonna draw the arrow, you're gonna bring the plotting compass over here again. You are gonna put the south pole on the north pole and you're gonna see to which direction is the north pole gonna go. So it might go down, I don't know. So here's south pole, north pole. Okay, then you repeat the process. You're gonna draw the arrow of the north pole. You are gonna get a new compass. You are gonna put the south pole on the arrow that you just drew and you're gonna see where does the north pole go, like this. And this is how this is the method, or one of the methods used to map magnetic fields. Now, question number 17. The diagram below shows a small compass needle placed on a bench under the influence of Earth's magnetic field. A bar magnet is now placed close to the compass in the position shown by the dotted line. Draw a new diagram to show the new direction of the compass needle. Explain. So very simply, when you put the compass, the magnetic field of the compass is going to be way stronger than the magnetic field of the Earth. Okay, since it's like way easier to control, all right? So that means what we are going to do is we are going to draw the magnetic field. So it's going to come like this, then from north to south, okay? And it's entering like this and exiting like this. So if we put a compass like this, it's going to be following this direction. If you put a compass here, it's going to be following this direction. If you put a compass here, it's going to be following this direction. And finally, if you put a compass over here, it's going to be following this direction, which is where the arrow is pointing. Now, that is it for question number 17. We move on to section 3.8. They said, explain how radial fields are used in the construction of current meters. Very simply, all you are going to do is you're going to explain how a current meter is built. So all you need to know actually is how the current meter is built. It is a U-shaped magnet with a ball or a sphere or like a concave thing, a concave sphere, let us say, okay? And then let's say this is north-south. The magnetic field is gonna go on like this, going to go through this. So this is called what? This is called planar, or from the plane. So planar radial magnetic field. Okay, so what happens exactly is that this magnetic field is trapped, or another word is shunted, okay, into this sphere or cylinder or whatever you want to call it. Okay, so it creates a planar radial magnetic field, okay, or not specifically planar radial, it was planar something, it was, here we go, it was plane symmetric radial, it was plane symmetric radial magnetic field. Now, what exactly does this field do is that it causes a tangential push on the current, okay? And then this is how it will measure the current of meters. So very simply, a current meter is a U-shaped magnet, and inside the magnet there is a sphere. This sphere causes the magnetic field to be plane symmetric radial. Now, because of the plane symmetric radial, okay, first of all, how does it become plane symmetric radial? It's because of the sphere. We say that the magnetic field is shunted into the sphere, it's trapped into the sphere. Okay, and because of this plane symmetric radial magnetic field, there will be something called a tangential push that will help it measure the current of whatever you are going to measure. Now explain how radial fields are used in the construction of a loudspeaker. So I'm just going to try to get an image. All we need to know about this question is that this is the first armature. This is the second armature, and this in between is what? This is the ring magnet. Now, because of the force of magnetism and whatever, there will be a constant attraction and repulsion, and this will cause for there to be a banging of this permanent magnet on a cardboard over here. Okay, and this cardboard will like bounce because it's elastic. It will bounce back and forth, back and forth, back and forth, and it will vibrate. Okay, and this vibration is gonna cause what? The sound. So very simply, that's all you need to know. Okay, now the fields in a loudspeaker, they are actually radial magnetic fields, and this is pretty much the difference. Okay, so moving on to section 3.9, how should we store magnets? Okay, how can a magnet be demagnetized? There are many ways to demagnetize a magnet, whether you heat it, or you store without soft iron, store without keeper, without its soft iron keeper, or you drop it, or you knock it, or drop with 2p, sorry, or you knock it, or you pass an alternating current if it is an electromagnet. You know, these are like the main ways in how you can demagnetize a magnet. So we move on to number 21. Describe a simple method to prove that the magnetic field around a wire through which an electric current passes changes when the current is increased. So a very simple experiment is that we will get a wire, okay, we will place it through a stiff card and we will pass a current through the wire. We will sprinkle some iron fillings, not necessarily only iron fillings, it can be like some paper clips, stuff like this, whatever, okay, over the card, and we are gonna increase the current passing through the wire, okay. After that, you will see that the iron fillings or the paper clips or whatever you put is gonna like be attracted more. Now, to detect the change, or to prove that the magnetic field changes when the direction is reversed, you're just gonna be using a plotting compass, and you will see, okay, if you're gonna put the current in this way, okay, let's say the current is going like this, it will go like this. If the current is going like this, you will see it change to this, so you know that the magnetic field is changing based on the direction of the current. Okay? So, number 22 grid, they told us, draw a diagram to show the magnetic field pattern around a straight wire carrying a current into the plane of the picture. State the rule you use to determine the direction of the field around the wire. So basically, you can have a current going into into the plane of the paper by denoting it by x. So this is the current, and the x means that it is inside, okay? Now, how do we determine to which direction it is moving? We're gonna place our thumb inside of the field or towards the paper, and we are gonna turn our fingers. As you can see, your fingers are gonna turn in this direction. So I don't know if I can demonstrate it, but like, put your thumb on the X, turn your fingers, you will see that your fingers, or the tip of your fingers, are going to which direction? They are going to this direction over here. So that means this is the direction of the field around the wire. So it is a clockwise direction, or in the direction of a clock. Now we use the right hand rule to determine this direction. Now, last but not least, what are the factors that affect the magnitude of the magnetic field created around a current-carrying wire? We have two that we should remember. So the magnitude of the magnetic field is denoted by B. It is directly proportional to the current flowing through the wire, and it is inversely proportional to the distance from the wire. So the farther the distance, the weaker the magnetic field. But the closer the distance, or like the less the distance, the stronger the magnetic field. If you increase the current, magnetic field is gonna increase. So that is pretty much it for today. Thank you guys for watching. I hope you enjoyed, and have a wonderful day.